Greetings, Dr. Dan with Optimal Optics, here to introduce Unit 14, Microscopes, Telescopes, and the Magnification of a Magnifying Glass. We will start with microscopes. I have here a ray tracing through a microscope. It has two lenses. The lens closest to the slide is the objective, and the lens closest to your eyes is called the ocular or the eyepiece. So I placed an arrow to represent the object. This would be where the slide is, and we send a ray through the optical center of the objective lens that forms an image, inverted image, at the primary focal point of the ocular. Because that now becomes the object for the ocular at its focal point, its rays come out parallel. They may not quite look parallel, but take my word for it, they are parallel rays. That triangle is the Greek letter delta. It's the distance between the secondary focal point of the objective and the primary focal point of the ocular. And in most microscopes, it equals 160 millimeters or 0.16 meters. The power of a microscope equals minus delta F1, F2, and the magnification of a microscope is minus delta F1, F2 divided by 4. So F is the microscope power, F1 is the power of the objective, F2 is the power of the ocular, and delta always must be in meters. Very important. There are different types of telescopes. One is called a refractor, also called a dioptric telescope. And in that case, the objective is a lens. A reflector telescope, also called the catoptric telescope, has a mirror as the objective. Now, there are three different types of refractors. There's an astronomical or Keplerian telescope, which has 2+ lenses, and they will form an inverted image. There's a Galilean telescope, which has 1+ lens as the objective and 1- lens as the eyepiece, and that forms an erect image. And there's a terrestrial telescope that has 3+ lenses, where the central lens, called the relay lens, re-inverts the image, and we get an erect image for that type of telescope. So the top has a ray tracing through an astronomical telescope with the objective lens on the left and the ocular or eyepiece on the right. And you'll notice that the secondary focal point of the objective lens is in the same place as the primary focal point of the ocular. Okay, the object for a telescope is obviously at infinity. It sends its ray toward the objective, which focuses the image at its secondary focal point. That becomes the object for the ocular at its primary focal point. Therefore, the ocular refracts the light rays parallel to each other. For the Galilean telescope, there is a convex objective lens and a concave eyepiece, and again, the primary focal point of the eyepiece coincides to the secondary focal point of the objective. This time, though, they are on the right side of the concave lens rather than between the two lenses. Again, we're looking at an object at infinity. This is a telescope after all. And the objective will refract those rays toward its secondary focal point. They never get there because the eyepiece refracts those rays. It uses the image that would be formed at the secondary focal point of the objective lens as its virtual object, and it sends the image rays parallel. The magnification of a telescope equals minus FO over FE. That is the negative focal length of the objective divided by the focal length of the eyepiece. So you see, you want the weaker lens to be the objective so that it has a longer focal length, and therefore you'll actually get some magnification. If you turn a telescope around and look at it the other way, you're actually going to see smaller images, which defeats the purpose of a telescope. You'll notice a telescope has no power. That's because it has an infinite focal length, and power equals 1 over the focal length. So we talk about a telescope's magnification. We do not talk about a telescope's power. This is a ray tracing through a terrestrial telescope. Terrestrial telescopes are used to look at things on Earth, which you want to see right side up. Doesn't matter if Jupiter is upside down, but it does matter if something on Earth is upside down. So there's a relay lens that's placed in between the objective lens and the ocular lens. The secondary focal point of the objective is at twice the focal length of the relay lens, and the primary focal point of the ocular is at twice the focal length of the relay lens. If you recall your thin lens formulas, when an object is placed at twice the focal length of a plus lens, the image is formed on the other side of the plus lens, also at twice the focal length. The object and image are the same size, but one is flipped. So therefore, when you're looking through the eyepiece, you are seeing a right side up image. Terrestrial telescopes are very popular among peeping toms. I saw a peeping tom looking through my window the other night. I was a little upset when he reached in and pulled down my window shade. Now, when you are using a magnifying glass, if you're curious about what the magnification is, the magnification is equal to the power of the magnifying glass divided by 4. Most magnifying glasses have their magnification printed on them or on the box that they come in. And so it's a simple matter to determine the power of the lens by multiplying the magnification times 4. If you own a set of binoculars, you'll see there are 2 numbers on the binoculars separated by an X. The first number is the magnification of the binoculars. The second number is the diameter of the objective lenses in millimeters. So the bigger that second number, the more light is captured by the binoculars. And of course, the bigger the first number, the more the magnification. So for example, a 6x30 binoculars has a magnification of 6x, and the objective lens is 30 millimeters in diameter. I'm going to construct 2 telescopes using lenses from my trial lens set. Every optometry school student buys one of these sets in their first year. There are spherical lenses, plus and minus, going up to 20 diopters. There are cylinder lenses, plus and minus cylinder lenses. There are prisms and assorted other lenses. I had the misfortune of opening this case up upside down in my first year of optometry school. That was the first and last time I ever did that. I have here a paper towel tube that measures 28 centimeters in length. I do apologize for the morbid advertisement on the ruler, but this is the only metric ruler that I could find. You have to wonder what body parts the mortician is using this ruler for on the job. But I'm going to use this towel tube as a telescope. So I'm going to put the objective lens on one end and the eyepiece on the other. And remember that the secondary focal point of the objective coincides with the primary focal point of the eyepiece. And the distance between these 2 lenses will be 28 centimeters. So there's an infinite number of combinations we can use. Let's let the objective power equal plus 5.5 diopters. So therefore, the focal length is 100 over 5.5, or about 18 centimeters. So if we subtract 28 minus 18, we get the focal length of the eyepiece has to be 10 centimeters, and therefore its power must be 100 over 10 equals 10 diopters, plus 10 diopters. So those are the two lenses we're going to use for our astronomical telescope with the towel tube. We can also calculate the magnification, which equals minus FO over FE. So it equals minus 18 over 10, and we should have a 1.8 times magnification. So we're looking into my neighbor's backyard. We're looking at his tangelo tree. I'm very tempted to pick the fruit when it's nice and ripe, but I exercise willpower and don't do that. We're seeing the brightly colored flowers that will become the fruit shortly. So I'm going to hold in front of the video camera my astronomical telescope with plus 550 as the objective and plus 10 as the ocular, and you can see it does in fact magnify the tree. So for our Galilean telescope, there'll be a convex lens in front as the objective and a concave lens in back as the eyepiece or ocular. Again, the secondary focal point of the objective is in the same place as the primary focal point of the eyepiece. There's an infinite number of combinations of lenses we can choose. Let's let the objective power equal plus 2. Therefore, its focal length equals 100 over 2, which equals 50 centimeters. So this distance is 50 centimeters. That means that the focal length of the eyepiece is negative 22. Remember, it's measured from right to left, the focal point to the lens. So the eyepiece's power is 100 divided by negative 22, which equals about negative 4.5 diopters. The magnification of this Galilean telescope minus FO over FE equals minus 50 over minus 22. It's going to be about 2.3x. So I've taken a plus 2 lens and a minus 450 lens out of my trial lens set. Place them on opposite ends of my paper towel tube. I'm holding them in front of the video camera lens, and you can see, in fact, we have magnification, and it does look like there's more magnification than with the astronomical telescope previously, as we calculated.